compound. Next slide. Next slide, you see. Okay, so we have studied in my previous lectures for coordination compound from complexation. Complexation is a reaction, okay? But it is a reaction for forming the complex. You have a metal, remember, you must have ligand. So ligand is specifically used in inorganic chemistry in coordination compound, and the complex form is always metal in the center and surrounded by the ligands. So the number of ligands attached to the metals play a very important role in coordination compound. So there is a nature of the ligand of the metal, which are transition metals, and the nature of the ligands. So we have learned the ligands can be monodentate, meaning the ligand attached to the metal. The ligand can be bidentate, meaning the ligand attached to two bonds to the metal. And they can have more than two bonding, more than two bonds, maybe 5, maybe 7. We call it multidentate. Okay, so this is the big difference between inorganic or coordination compound compared to the organic substitution reactions. So, but here we are studying substitution reaction of the metal complexes. Okay, we have studied how to make complex. Now you want to study the reaction of the complex compound, the reaction of the coordination compound. Okay, get that picture correct. Next slide, please. Okay, what are the reactions that can take place in coordination compound? Basically, there are 4 types of reactions. Number 1 is the substitution reaction. Okay, many of the reactions are substitution reactions. So this is your complex MLN, and is ligand, L is ligand, and then you have another group react with the complex and replace 1 or 2 of the ligands, and the ligand in the complex 1 or 2 will be leaving the complex. So this is a substitution reaction. Many of the reactions are substitution reaction. Okay, for example, this is a hexa aqua ion. You react with the ACAC ligand. So 3 of the ACAC group will go into the coordination, and all the water molecules are removed, are replaced. So we have 3 ACAC ligand attached to the ion. You remember, ion have 6 coordination, and you have 3 here. So from here, you know the ACAC ligand is a bidentate. So bidentate, you got 3, it becomes 6. So the coordination remains 6. Okay, so there is much more chemistry for coordination compound compared to the organic compound. So you have a metal, you have a ligand, and replacement take place at the metal center. All right. So this is again another example. Copper sulfate. You know that copper sulfate or other metal complexes or other metal salts will dissolve in water. The first thing happen is the aquation, not hydrolysis. Hydrolysis can take place, but aquation, the water molecule attached to the metals. So you react with ammonia. So remember, this sulfate is not in the coordination sphere. It is outside. It's a counter anion. Sulfate 2-. Therefore, your copper complex must be 2 plus. Okay, so when this 2 plus to balance with 2 minus, so your copper must be copper 2 because water is neutral. Okay, so ammonia, for the ammonia, we replace the water molecule, and then and your 2 water molecule will leave the complex, leaving only 2 water molecules. So this is a replacement reaction or sulfate or substitution reaction. And the nature of the complex remain the same. The sulfate is the counter anion. So from the reaction, you can tell what happened in the reaction, and you can describe the reaction. This substitution, sulfate remain counter anion, and your ammonia replacing the water molecule. Okay, that is substitution reaction. But it's also good to know there are other reactions as well that can take place. Can happen to the coordination compound. One is addition reaction. Addition reaction means aduk, mix together. So the complex form bond with the new ligand and making a new compound join together. So if you started with N ligand, now it becomes N plus 1. Okay, that's called addition. You can also have dissociation, the reverse of addition. For example, if you hit the complex, one of the ligand will be leaving the complex, so it dissociates. Okay, then you have addition and dissociation reactions. Number 3, as you know, metal ion can undergo oxidation and reduction. Okay, oxidation reaction involve electron transfer. Oxidation is the loss of electron. Reduction, you receive electron. So that is a electrochemical reaction. That's a redox reaction. And the fourth one is the reaction at the ligand. So substitution is a replacement at the ligand, but there are also reactions that can take place at the ligand. So these are the 4 common type of reaction undergone by the coordination compound. And today, we will focus on the substitution reaction. Okay, next slide. Okay, I always ask the student, before you start something, you must ask yourself, simple question, what it is. Some students can talk about reaction, a lot about reaction, but when asked about simple question like what it is, then they have a problem. Okay, so for reaction study, we must ask ourselves, what is the reaction? Is it redox? Is it substitution? That's number 1. All right. If you know it is substitution, then we ask ourselves, how does it happen? How does it happen? Or why it's happening? Okay. So with all these questions, we will tell you the story of the reaction, tell you the whole process from starting to the end about the reaction. Okay. So you have to understand in a chemical reaction, as I said, bond breaking, bond formation. And having all this knowledge, we can write something about the mechanism of the reaction. So when you study reaction, you have to know what the reaction is. So when I said to know the reaction, you must be able to write the equation of the reaction. It's not easy. If you read book, it's fine. But if the reaction is new, you have to study. So those of you who are doing final year project, study new reaction, you have to find out what are the products, what are the equations. If the reaction is stoichiometric, so you have to study the whole thing about the reaction. Stoichiometry. Stoichiometry means maybe 1-1 reaction, maybe 1-2 ligand. So you establish the stoichiometry. Okay. So at the end, we are very interested to know the mechanism. Why should we find or study or to know the mechanism? From the mechanism, you can use it for stimulating the reaction. So if you are engineers or working in the pilot plant, production line, knowing the mechanism, you can control the reaction. Therefore, mechanism is very important. Okay, it is mathematics involved. So in order to study the mechanism, these two subjects, thermodynamic and kinetic theory, is very important. I remember in ITB Bandung, Allahyarham Pak Susanto. So he is a theoretical chemist and teaching thermodynamics. The student always laugh during the lecture because so many mathematics. Okay, so that is thermodynamics. But thermodynamics is very important for chemistry, for physicists, especially for mechanical engineers, because mechanical engineers involve energy transfer from the steam, from the reaction. So thermodynamics is very important. So thermodynamics can predict whether the reaction will take place or not. So you remember when you learn thermodynamics means something to do with heat, the energy and the heat. So you measure the enthalpy, you measure the entropy, and you can also calculate the activation energy of the reaction. That is thermodynamics. So because this is very important when you study the mechanism of the reaction, particular substitution reaction. Okay, but thermodynamics cannot tell you how slow, how fast the reaction. So you want to study the speed of the reaction or the rate, you know, from experiment. So I was told that you have learned kinetic studies. Is the line okay? You see, line is okay. Okay, thermodynamic and kinetic studies. So get this basic concept when we study the mechanism of the reaction. Okay, next slide. Okay, one advantage of studying complexes reaction, the complex is colored. So complexation or coordination compound is about color chemistry. So you can use your naked eye to study the chemical changes, study the chemical reaction using naked eye. But naked eye is not sufficient enough to get the proper data to describe your research. So you have to use some instrumentation in your study. But color is a very useful way to indicate that reaction is taking place. So most of your transition methods are colored, okay? So we can make full use of this color to study the reaction. The next slide. So I'm still talking about get a picture about reaction, okay? And one of the very important to remind you again, when you dissolve a metal, a salt in water, the first thing will happen is the equation, the water molecule. Always remember this. Water molecule will become ligand and attach to the metal. Now you can also do not necessarily in water, in ethanol, in methanol. So the methanol will become the ligand. Okay, so then you have a study in non-aqueous system. So today we only focus on aqueous system, right? So the first thing must remember, what are the species of your metal complex in water? Always aqua, okay? And then there must be some degree of hydrolysis. So you have to study the behavior in aqueous solution. Sometimes the species depend on the pH. So here you can see iron, you have hexa aqua, which is iron 2 plus. You can also have iron 3. You can have iron 3, then the charge will be different. Okay, and the color also different. Cobalt, copper. So the whole range of metal salt in water. Okay, so you can use this link. And this was studied by Alfred Werner in 1930. So if you look at the thesis in 1913, yeah, I was not born. You are all far away from 1913. Okay, you will find a PhD thesis, S3 thesis, only 3 reactions. So if you study 3 reactions, you get your S3. Because during that time, instrumentation are very limited. You use naked eye, you use pH meter, you use conductometer. So when I was in Oxford University, I saw many old theses. I tend to laugh because it's so simple presently now, but not during their time. So their time, like chromatography, they use big column and column material. That's all. So today, your column chromatography has special pump connected to your UV. In 1913, no such thing. Okay, so that is something to tell the new generation. The new generation are so handy, available with electronic gadget, everything. So it become more sophisticated. Yeah, but in old day, no. So as I told you, one S3 student only study a question, yeah, to determine what are the species of the metal ion in water. PhD, S3. Okay, but today is very well established. It is in the book. But when you do your final your project or S2 or S3, you must have some new ideas. New ideas mean new problem. Yeah. So you do not know. So you have to do research. Okay. Now, understanding the equation, must remember always go for equation first. What are the species of your coordination compound in the solution? Either water, methanol, DMSO. Okay, they are all potential ligand. Okay, next slide. Okay, now we go to see some examples. Okay, so I will touch very basic. The detail again, your good docent will go into the detail. Okay, I'm trying to emphasize the concept, the basic is very important. So any problem, you go back to the basic. Okay. So as I said, substitution reaction in coordination compound is the replacement of one ligand, okay, but not necessarily one ligand. It can be 2, it can be 3, by another group of ligand, okay, not in the complex compound. It's from outside. So just to see an example, if you dissolve copper sulfate in water, what happens? You will have a pale blue solution, hexa aqua copper. So this is very important. This is very different structure of copper sulfate in the solid state. In the solid state, it's very different. Okay, no water. Okay, so the copper and the copper in the solid state are packed together. They may form link. Yeah, the structure in solid are very different than in solution, in water. In water, you have an equation. The French guy say equation. So if you write your nomenclature, your picture in the connection compound, I always remind, don't forget, you write with the bracket, meaning connection compound. If a copper, we have 6 water molecule as ligand, electron is shared to the copper, and the whole complex is 2+. Water is neutral, therefore your copper here is copper 2+, oxidation state. Okay, so if the student really understood this, you have no problem to answer question. Okay, so in the process of learning, this is what you have to learn first. So what happened during Wagner time? You react this hexa copper. Knowing the hexa water, hexa aqua water, at that time, is a big achievement. It's a success. Okay, you get S3 for it, right? So now, what happened when you react this hexa aqua with ammonia? Okay, it depends how you do it. If you put a lot of ammonia, you will see dark blue formation. So then again, as I told you, you have to determine what is that dark blue compound. You do analysis. So how did they do the analysis in the old days? Where they have to evaporate, give you some solid, and then they analyze the compound. May take 1 month, okay, if you're lucky. So at the end, they got this product. You know, they got 4 ammonia, replace 4 water molecule, and there are 2 molecules in the complex. You got this dark blue. But if you add ammonia drop-wise, drop by drop, drop by drop, okay, this is the chemist's work. The chemist is there is an art. When you do research, we call it, there is an art to do research. You don't rush. So we try to observe in different ways. You add drop by drop, see what happened. If you drop in excess, is what happened. All this will give you very important information. So you all chemists must develop this kind of culture of curiosity. What happened with a small amount? What happened with excess amount? Blah, 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 okay? So what happened? They see the change. When the pale blue of the hexa aqua, you add small amount of ammonia, you got a precipitate. And that precipitate is a hydrolysis reaction. So it's a copper hydroxide. You see the precipitate. So when you add more ammonia, the precipitate dissolve. Okay, give you dark blue solution. So now you can describe. First, it gives you copper hydroxide, which is hydrolysis, and then you add more, the precipitate dissolve, it gives you a new complex. So you can describe this substitution reaction involve 2 stages. So the first one can be intermediate, because when you add excess ammonia, you don't see the precipitate. Okay, you have slowly, you see the precipitate. You have excess ammonia, you don't see the precipitate. Meaning the precipitate is formed very quickly and it dissolves very quickly. You don't see in excess ammonia. So you can then write the equation of the substitution reaction. So you can look at the right hand side. That are the reactions. So this is S2, okay? During the old days, this is S2 research. Okay. Now, as I told you, coordination compound, unlike organic molecule have a center of symmetry. In organic, you have your stereochemistry, you have your geometry, and you learn, remember, your transition metals. You have to know that is it D1, D2, D3, D4, D5, or D6. They will tell you the geometry. So in this case, it is octahedron. Then you know the reaction is a big achievement. Then you have to describe how the substitution take place. Is it take place at the axial position? Is it at the equatorial position? Then you have studied the stereochemistry. Okay, so this is the beauty of substitution reaction in coordination compound. Okay, this is the copper. Copper is a very classical example. I like this copper sulfate because everybody know copper sulfate, the blue color. Okay, now we go to, I hope you got a picture now to study the reaction, to study the stoichiometry of the reaction, and from there, many more questions and curiosity. Okay, so you go see next slide. Let's look at another example. What happened when you add copper sulfate in the acid? You put acid into it. So when you add acid, you know, HCl, HCl will give you hydrogen ion that will change the pH, and you have the ligand Cl minus. Okay. So what happened is, in this particular reaction, all the water is replaced by chlorine. And when you do the analysis, there are only 4 chlorine, not 6, only 4 chlorine. Then as a chemist, you will ask yourself, why 4 chlorine? In the previous example, copper sulfate with the ammonia, you can have 4, coordination maintained is 6. No, coordination is different. It's 4 coordination, okay? No longer 6, okay? And all the 6 water molecule is replaced by 4 chlorine. So replacement of ligand is not necessarily 1-1. So in this case, 4 chlorine replace 6 water molecule. So when you have 4 chlorine, the geometry change. So this is an example of substitution reaction where the geometry of your reactants, starting material, and the final products change, are different. So in your first copper is octahedral, it gives you a yellow product, which is tetrahedral. So there's a change in the geometry from octahedral to tetrahedral. Then you ask yourself, why? Why this is happening? Okay, so after regular students have studied this, they write the equation. Okay, this question is very valuable, as I told you. In the 1918 is a S2 material or S3 material, but not today, because you can read from the book. So you establish the reaction. Reaction will explain what happened in the reaction in the solution, and you can also study or predict or think what happened to the geometry is changed from octahedral to tetrahedral. By now, when you have tetrahedral, you must know the angle between the ligand, just like methane. A chemist who doesn't know the angle of the ligand to the metal center, I'm very sorry, you fail my paper. Okay? So tetrahedral is always 109 degrees. Please remember that. And octahedral vertically is 180 degrees. In the equatorial position is 90 degrees. So for octahedral, it's very easy, it's simple to remember. But tetrahedral, you learn organic chemistry, you must know it's 109 degree, then they call it tetrahedral. So now let's answer the question, why only 4? So to explain this, because there are many factors. Now we know there must be factors to influence the reaction, in particular substitution reaction. One factor is the charges and the size, because the size of chlorine ligand compared to the water, the chlorine has much bigger size, because remember the chlorine is on the right end of your periodic table. So the size is big, cannot go, no 6 chlorine can go into the coordination sphere. So now here is size is very important. So adding you more information, more story about the influence of size. Okay, this is 2 example of copper sulfate. Of course, there are many reactions being studied with copper. So I believe during that time, if you do S3 or PhD, at least you have to do 10 reactions. Masters maybe 2-3 reactions during that time. Okay. So now we go to the next slide. So we have discussed about copper. Now let you see chromium, because chromium also very common solved in laboratory or even in everyday life. Yeah, chromate. Okay. Again, remember in water, chromium will form aqua, hexa aqua. So meaning octahedral. So when we make questions in the exam, we never told you what is the geometry, because from the formula, you can know the geometry, because the 6 ligand, therefore it must be octahedral, okay? And the color is purple, and water is neutral, okay? Therefore, the charge is known to be 3+, therefore your chromium must be 3+. So this is chromium 3, purple. But this is quite different compared to the copper sulfate, because chromium sulfate, when dissolved in water, it is purple. You can see on the right side it's purple. But after some time, it turns green. Okay. So what is that green color? As I told you, the good part about coordination compound is that it has color. Color indicates the changes, the chemical changes. So what happened is, when they studied this, they found the water molecule, the water ligand, has been replaced by the sulfate. Remember, your copper, your chromium sulfate is outside the sphere. Sulfate is a counter anion. But in this case, the sulfate replaced one water molecule, it becomes 5, and then you have sulfate. Okay, so this is very special properties with chromium sulfate in solution. It changes from purple to green. Okay, so then you study the reaction with chlorine, with ammonia. So we learn, you get more information, just like when you did with copper sulfate. Okay, but the species, the starting species is the same, hexa aqua. All right. So this is chromium. So now you have studied the substitution reaction, the speciation, and behavior in water solution. Okay, you have to make sure you get this species in water correct before you start answering question or start study the reaction. All right. Now let we go to the next slide. So the next slide is we we try to learn more. Okay, next slide. Okay, you have colored, you can use your eye, but using eye, you cannot show to the people the real data. So in the last lecture, I've shown you the spectrophotometer, UV visible, is very useful for studying colored compound. You can take the spectrum. Now, instead of using color, or you take photograph, you show the color changes, you can use spectrum to describe your reaction, okay? So I've shown you these UV spectrophotometers in the last lecture. There are many companies now from China, from Japan. US now become very expensive, so people buy from Japan or from China, okay? So we can use instrumentation to study the reaction. Next slide. So I've shown this in my last lecture. When you study the spectrum of the chromium complex, in this case, the ligand is chlorine, another 5 ammonia. This is octahedron, okay? The coordination number is 6. So you have a maximum peak here, 1, 2, and 3. So from spectroscopic study or point of view, you have learned to assign what is this peak. Okay, don't forget, UV energy is strong enough to excite the electron. So it is electron excitation. So from this peak, you can identify your compound. From this peak, you can measure the extinction coefficient, the epsilon. So you can make calibration graph. From the graph, if you have unknown solution, you can calculate the concentration. So that is Beer and Lambert law. So this is very useful technique to study reaction, to study properties, and also spectroscopy to describe your theory, your calculation from theory. Remember, you have ligand field theory, electrostatic theory, blah, blah, blah. There are so many theories. Okay, so I'm sure in your lab, you have this UV machine. Chemists must have this UV machine, maybe more than one, more than two, maybe more than three, okay? So next slide, we are using instrumentation now. As I told you, when you study the reaction, I revise again. This is a new reaction, not in the 1980, in 2017, okay? The ligand, all the easy ligand, chlorine, bromine, acar, that's all time ligand. So for us, we have to do something new. You make new ligand. I remember when you did a PhD with Ibu Julia Ongo, he made new complexes, new ligand. Okay, so to identify what are the new compound, what are the product, may take 1 semester. It's not a 1 day or 1 week work. It may be 1 year work. So in this study, my PhD student tried to use a cyclic ligand. You can see this is cyclic ligand. So the ligand itself form 4 bonds at the equatorial, and another 2 is formed at the axial position. So this takes time because to study the reaction, to study the product, it's not easy to identify the product. Eventually, he got crystal. And my God, thanks God, I know about X-ray crystallography, which I'll give you lectures in ITB Bandung. We can identify what actually the molecule from molecular structure point of view. And the UV. So from here, we can study the reaction, complexation. We can study the reaction of the complex. Remember, complexation is a complex formation. Complex substitution is a reaction on the complex, on the conjugate compound. Okay, so when you have this complex, you react with isothiocyanate. So the ligand isothiocyanate is very interesting because the attached to bonding to the metal can be through nitrogen, can be through sulfur. Okay, so this kind of behavior, there is a terminology for it. Suddenly I forget the terminology here. But anyway, you can have ligand through the isothiocyanate. Okay, you can have ligand through the sulfur. So either sulfur attached or nitrogen attached. Okay, so next slide, you will see how we study the reaction. Okay, again, we use UV. We have chromium chloride. So we react with the ligand. And remember, chromium chloride, when you dissolve in water, what happens? Okay, there may be some aqua. You have to know the species. And you can see here, there are two peaks, UV peaks. Okay, UV peaks. One is here, and one is here. You are at the higher wavelength. Higher wavelength means low energy. Here is high energy. So when you add the ligand into the chromium, you will find at this peak, this maximum peak shift to the right. When it shifts to the right, meaning a new species, a new compound is formed. But here, there is no shift. Okay, but the absorbance or the intensity is going down. This is a repetitive scan. You repeat every, let's say 1 minute, every 2 minutes. So you can see the reduction of intensity here. And in here, there is a shift. After shift, then the shift may stop and then it increase in the intensity. So from this behavior, you can describe chromium plus ligand, form a complex, and finally give new products. So this complex is an active complex, dynamic complex. Okay, the formation, how fast is the formation? This is called reaction scheme. So when you do reaction in the complex compound, you have to look for the reaction scheme. What happened? That's why I said when you do reaction study, what happened? You must be able to explain what's happening, either using your naked eye or using the instrumentation. So when you look at the spectrum, you will find the changes here, the change intensity is significant. And here, there is a change in intensity, but very small change. So this will be good for you to study the kinetic, to study the reaction rate. So you have learned about kinetic theory. Kinetic means study the rate, study the change in the reduction time, and then the theory you learn about first order reaction, second order reaction, pseudo first order. You can prove by making this kinetic plot. This is a first order reaction, log. Change in absorbance with time give you straight line. So you know that this reaction is a first order reaction. So this is what you learn in kinetics. Okay. Now I've discussed to you about getting more knowledge on the reaction, and then you can also study the rate of the reaction. You can study the kinetic of the reaction. Remember, when you want to describe the mechanism, all this information are very important to establish the mechanism, what happened in the reaction, study the thermodynamics, study the kinetics. Okay, thermodynamic can predict the reaction can take place, but thermodynamic cannot tell you fast or slow. You have to do kinetics. Okay. So next slide. So now to study the mechanism. As I told you, I only explain and try to discuss with you the basic, the detail. Your docent will discuss more in more detail. Okay. So if you want to study the mechanism of the reaction, what kind of mechanism? Somebody say, yes, substitution is mechanism. Of course, you can say that. But the question is, substitution will tell you the type of reaction, but doesn't tell you how. How does it happen? Okay. So you can think possible way this thing can happen. So you know that the substitution is taking place at the center of the complex, at the metal center. There are two possibilities of replacement. One, the new ligand come and attach to the metal center. Okay, that is called associative. The new ligand join the complex, they associate together. If they associate permanently, we call it adduct. Okay, so second way is one of the ligand leave the complex. Okay, leave the complex. Then the new ligand come in. So basically, there are two ways of substitution. Just like the military, the TNI, Tentera Nasional Indonesia. If you enter the military camp, there will be a guard house, you know, with a weapon, with a gun. So this guard man, the Surawangi military, they work from 8, maybe 6 o'clock in the evening. At 6 o'clock, a new platoon will come in. So there are two ways this new platoon will come. One, the guardman leave the guard house, or the new platoon came to the guard house, they talk together, and then the previous guardman will leave the guard house. So this is the idea of replacement reaction. So what I want you to focus is, look at these two mechanisms, the associative mechanism, the dissociative mechanism. We call it when the new ligand come and join the group, associative. When the ligand leave the group, the new ligand come in, that is dissociative. But the Americans have more ideas. Okay, they also consider at the interchange, at the guard house. What happened at the guard house during the interchange? So this is the American way. Okay, and now I don't want to confuse you. We only focus on the associative and dissociative. So when you do research, you do your S2, you can learn more about this interchange. Okay, for undergraduate, I think it's enough for you to understand. You can see, you can think, you can visualize associative and dissociative. Okay. Now, when you learn reaction, you learn about reaction profile. When I mention reaction profile, is the energy changes from starting to the end. So all chemists know about this reaction profile, okay, from thermodynamics. A reaction will take place by collision of molecule. They have to go through what we call activation energy, or in solution, they prefer to use transition energy. Okay, those who have this energy will undergo reaction and give you product. So this product may not be stable enough, and it forms the final product. So again, it goes through another transition energy. So this is called reaction profile. And you can study this from thermodynamics. Today, you have computer program, to study and predict thermodynamic behavior. So for this particular compound, we call it intermediates. Some intermediates are stable, you can detect. Some intermediate not stable, you cannot detect. So it only exists in theory, right? So if you see this kind of profile energy, you know that this reaction is two-step reaction. Step number one, giving you the intermediates. Step number two, the intermediate to give you product. Therefore, you can write the reaction scheme. So for associative, this is the scheme. The new ligand combined with the complex form a new intermediate. And then from this intermediate, it can dissociate, give you a new complex, and one of the ligand is removed. So you have to know this. We call it reaction scheme. I don't call it mechanism because, as I told you from the very beginning, mechanism is a complete picture, complete story, how it happened from starting to the end. Okay, so this is called reaction scheme. This reaction scheme is very important to start with. So, for example, the intermediate formation, the complex formation here, can be very, very fast, can be very, very slow. In some cases, it's slow. But the intermediate is converted to product very fast. So you can write the reaction scheme. So this reaction scheme, you must know. How do you know? From the information you can get from the book, you can look from online. So now all information are at the fingertip, the jari saja. So this is slow, this is fast. If this is slow, you can monitor, you can follow, you can study the kinetics. This is very fast. You cannot measure the kinetic, but in the mechanism, you can always consider this step in the mechanism. The mechanism means you can use the mechanism to prove from the kinetics. You have to prove your mechanism using kinetics, using thermodynamics. Okay, so when study reaction means thermodynamic kinetics is very important for you to understand the basic principle. Fortunately, you have learned kinetics. I was told that you have learned kinetics, you have to learn thermodynamics. Study the enthalpy, study the entropy, study the energy of reaction, okay? Now, associative, dissociative, okay? Next slide. Okay, I just want to show, I don't want to discuss all these aspects. There are many aspects of reaction, okay? When you start doing research on the reaction of substitution reaction. The new ligand has effect, the solvent has effect, the outgoing ligand also play important role. So there's many questions, okay? I just want you to introduce the metal, the kind of ligand, all play important role in studying the coordination compound, meaning there are many opportunities for chemists to do S2, S3, okay? Many opportunities. Okay, next slide. So the next slide, just to show you the interchange. I don't want to focus so much about interchange, okay? Interchange here means what happened at the complex formation between the new ligand and the complex. I've given you the analogy at the military guard house. So something happened at the military guard house. Normally the commander will give instruction, do this, do that, you go out, blah, blah, blah. So you know American is a country very proud of military. They always go war with other nation. So they use this concept of military analogy, and they call it interchange mechanism. So when the new team come in, the old team will leave the group. So interchange. So I don't want to go very detailed on this interchange. Just focus on associative, dissociative, because this will be proven by thermodynamic and kinetic. So thermodynamic and kinetic is already a difficult subject. So I don't want to go very difficult on the interchange. The next slide. Okay, this is just to show you again what happened during the interchange. So when you have associative, your coordination will increase. From 4 become 5, 6 become 7. So there is a change in geometry at the interchange. So you have to consider change in geometry. And finally, it will give you the old geometry from octahedron to octahedron. But at the interchange, many possibilities can happen. Change in geometry is one of them. So that is what I expect, where it's not difficult to think what's happening, but going into detail is difficult, okay? Not at your stage. Okay, next slide. So we have a change of geometry, okay? So next slide, we can see another important terminology in study the substitution reaction. The term is the ligand can be considered very inert or very labile compound. So what you mean by labile? What you mean by inert? So of course, labile means very movable, very active. One of your friend always go to other friend's house. He's very labile. And one of your friend doesn't like to go out, stay in the room, in the house. So he's not labile, okay? So in substitution reaction, the term labile and inert are very useful. So in this case, your copper again with ammonia, the reaction is very fast, equilibrium take place. Also your iron, you can see this is isothiocyanate, which is replace one water molecule. When you write like this, is the sulfur that attached to the iron, so thiocyanato. If nitrogen, then the name become isothiocyanate, all right? So these are very labile compounds. So iron here, hydrolysis product, OH, yellow. With acid, it become colorless with 6 water molecule. So it is a very labile compound. So in some cases, they are inert compound. So please understand the term labile and inert. This labile situation, you can also see when you study the kinetic behavior. So the kinetic behavior for labile, the rate constant will be higher than the rate constant of the inert compound. Okay, remember labile and inert. Next slide. So this is another situation where inert, labile, and stable, unstable. So I've shown you in the energy profile, you will find some intermediates are formed. That intermediate sometimes stable, unstable. Unstable means the intermediate form within second, within nanosecond. Okay. So there is a kinetic term for this concept: labile, inert, stable, and unstable. Stability is always thermodynamic term. I tell you, the intermediate is stable. That is thermodynamic. But the speed, you have studied the kinetic. Okay. So study the kinetic, normally labile and inert. Okay. Inert means maybe the reaction rate is slow. Labile reaction rate is faster. So this is another example. This complex with the ligand fluoro and 5 water molecule, it is a stable complex, meaning if you have this compound, this solution, the solution remain 1 day, 5 days, maybe 1 month, stable. But the reaction is labile, you know. The fluorine is small in size, therefore they're very labile. So again, this reaction scheme always very important. I told you from the very beginning, when you study the reaction, the first thing is to know what happened, and you can always write the reaction scheme. This is hexaamine cobalt with the hydroxynium ion. You in the presence of acid, pH is low. This is what happened. All the 6 ammonia will be replaced by the water molecule, and the 6 ammonia is replaced. You can study the thermodynamic. You find the gift free energy is less. So that means this reaction is very favorable, can take place. Okay, and unstable because the grip energy is very low. It can undergo reaction very effectively. Therefore, it's unstable. But the compound is inert. Okay, so you have now situation where the product is hexa aqua. Inert compound are easy to study because it is stable. Okay, labile compound depend. Some labile compound, because it happen very fast, difficult to study. Some labile compound, it happen at a considerable rate, you can still study. Okay, and then there is a general rules. Okay, relationship with LFSA. It is something to do with ligand field stabilization. So we have studied about the theory of ligand. We have crystal field theory, ligand field theory. They are all interrelated. Okay. So there are some examples of stable, unstable, labile, and inert complexes. Okay. So go and see the next slide. Don't forget, we are trying to establish the mechanism. Now, just touch a little bit about the mechanism again. You can classify them. So I just want to remind again, we focus only on dissociative and associative. And you can write the energy profile. These are the intermediate. These are the intermediate. You can see in some cases, the intermediate is formed very fast. Some cases, very slow, and the product very fast. So energy profile is an important thermodynamic property to describe whether the reaction is favorable or not, and making use of the gift free energy. Okay, next slide. Okay, now coming back to the kinetics. So when you learn about kinetics, it is about the reaction rate, kadar tindak balas, how fast, how slow. You have to measure the rate. So how about the reaction kinetic of associative and reaction kinetic of dissociative reaction? Okay. So when you learn kinetics, for any reaction, the first thing you to do is to establish the rate law, hukum kadar, the rate law. What is the rate law? So the rate law is the rate relationship with the concentration of your reactor. Actually, the formal definition is the relationship between the rate and the activity of your compound. Since the activity coefficient is considered 1, then the activity is the same as the concentration. So the rate depends on the concentration. You change concentration, you will change the rate. So we have to establish the rate law. What is the equation correlate the rate and the concentration? Okay. So now for dissociation reaction, here, you know that one of the ligand will leave first, then new ligand come in. So these are the reaction scheme, not yet mechanism. Mechanism is a complete description from reactant to the product, and you need kinetic to prove it. Okay, this is a scheme. So from this scheme, you can work out the rate law. So from this scheme, for the actual rate law, you have to determine from the experiment. Okay, so now you have a reaction scheme. So the reaction scheme involves equilibrium. So you have a rate constant to the right, rate constant to the left. When this rate constant established, you can have the equilibrium constant, the capital K. Okay, capital K equilibrium constant is equal to K1 divided by K minus 1. Okay, so this is the scheme, and then your new ligand coming, which is K2. So it will depend on the rate constant, whether this is bigger than this. Bigger than this means it's very fast, or it's slower than this, slower than K2, meaning this is slow, this is fast. Okay. Now, when you learn kinetic theory, you want to determine, or you want to establish the rate law. Using this scheme, you have to use one of the concepts called steady state hypothesis or steady state approximation. What it means is you have an intermediate. You do not know the concentration of the intermediate. No way for you to know, because it forms in the middle, in between. You can know the concentration of your reactant. You can know the concentration of your products, but it's not easy to know the concentration of your intermediate because you keep changing. So somehow you have to approximate. You have to approximate the concentration of the intermediate, okay, in order to obtain the rate law of this scheme, association scheme. So what they do is, this is your rate, which is concentration over time of your complex, meaning you follow the disappearance of the complex. And the rate law here is K1 complex, which is K1 complex, K1 step. This is formation of your complex, okay? At the same time, it reverses, so it becomes minus K minus 1 of this one become reactant, okay? So the reactant are ML5 and X, so this is 1. And also the entire scheme, you have ML5 become less and less, so it's negative. So the step is K2, and that reactant involves ML5 and Y, ML5 and Y, okay? So this is your rate equation of your reaction based on the reaction scheme. You may have a different scheme, okay? Then we have different rate equation. Okay. You know the concentration of ml5, but you do not know mlx. You do not know, you know the y concentration, but the intermediate you do not know. So you apply steady state approximation. What it means is steady state approximation means the rate change is almost zero, meaning the rate change or the rate of your entire reaction is the same, no change, approximately close to zero. So this is what you call, you apply a steady state approximation or steady state hypothesis. So from here, you can calculate the concentration of your intermediate. Okay, next slide. So let's see whether you get the formula of your intermediate. So when you apply the steady state approximation, you can determine the concentration of your ml5. Okay, remember this is dissociative D. So this is an equation of your concentration of your intermediate. So ml5x, this is your x, this is your y. So that is the rate. You can rewrite the rate law of your products. So your product is ml5y in the second stage is equal to K2 times y times NL5. So you find the rate law for your second stage is this. Then you replace your ML5. So you know the ML5 is this. You replace it in this equation. You will find the final rate law is this one, involving K1, K2, and K minus 1. Okay. So from this rate law, you do the experiment and see whether this rate law is in agreement with the experiment. Okay. So of course it doesn't look in agreement, but you change the condition of the reaction. Maybe one in excess of the other, and then from that you will come to the situation whether this is first order or second order or pseudo first order, and then you check from your experiment. Okay, so this is a process using kinetic to prove the mechanism, to prove this reaction scheme is correct, the right, agree with the kinetic experiment. Then you will say this reaction scheme is acceptable, boleh diterima. But if you can come up with different scheme and you find the kinetic agree, so your reaction scheme also will be acceptable. And then which one is correct? Well, you have to do analysis. Try to analyze, to characterize your intermediate. Maybe your intermediate doesn't really exist. So those are challenges in studying the mechanism. Okay. So now, applying the steady state approximation, you can determine, you can get the expression for your intermediates, and then you can do the rate law, and finally you end up with the rate law from your scheme. Okay. Now let's see the next slide. So this is mathematics. Okay. So now you can also apply the same at the interchange. As I told you, I don't want to discuss what at interchange. Just enough to discuss on the dissociative, associative. So we go next slide. Okay, so but you cannot run away. So this is a detailed mechanism, the mathematics of the intermediates. Okay, the kinetic equation can become more complicated. So I don't want to discuss in detail the mathematics of it. I just want to mention the final equation that is more meaningful to our approach, how to study the mechanism. Okay, let's go and see the next slide. So in the next slide, so this is what the final reaction rate equation. Okay, when you have this kind of final rate equation, then you can conduct the experiment normally in two different conditions. One is at low Y concentration. Remember, Y is your coming ligand. The concentration is low. When it's low, then you will find this and this can cancel. Or when it is low, the rate will depend on the initial concentration. So you will find the reaction rate is the concentration of your complex, the concentration of your coming ligand, because this is small, Y is small, you can ignore, then the reaction become second order, okay? So you have a situation where the reaction is second order. Second order means two molecules come together, second order. Now, if your Y is very high, meaning in the reaction, Y is very high, when Y plus 1, because Y is very high, it's almost like Y, okay? 1 is too small. Y is very high, so 1 plus high is high, almost no change. So what happened is the Y plus 1 initial, 0 means initial concentration, and the initial Y is about the same value. You have 10, you become 11. 10 divided by 11, if you compare 10 by 10, doesn't make a big difference, okay? So this Y cancel, this cancel top and bottom. You get K1 divided by K prime M naught. This is a first order reaction, depending on the concentration of your complex. So you have a situation where second order reaction and first order reaction. So second order reaction reflect two molecules, okay? That will be associative. And it only depends here in one reactant, the complex, then it may be dissociative. So you can differentiate between associative and dissociative from the reaction order. Second order always means associative. First order is a dissociative. Okay, next slide. So this is the concept that I want the student to understand. Okay, next slide. Okay, now previously I discussed about dissociative. Okay, for dissociative, we have two situations: higher concentration of Y, low concentration of Y, the coming ligand. It can be second order, it can be first order. But in the case of association or associative reaction, this is the reaction scheme. Okay, reaction scheme. You also apply steady state approximation because, as I mentioned, there is no way you can determine the concentration of the intermediate. You can use calculate using the steady state approximation. You will find in the case association, the final red ball is always involved the complex and the coming ligand, second order. So dissociation is always second order kinetic. Okay, this one you have to understand. Dissociation always second order. Dissociation can be first order, can be second order, depending on the concentration of Y ligand. Okay, so next slide. Next slide, you will see coming back to your other practice of complex, you study about octahedral substitution. Okay, I just want to mention again, when you study octahedral substitution, you can study the reaction profile, you can determine the activation energy, you can determine the overall activation energy from the thermodynamic. You can tell is thermodynamic favorable, and then study at the kinetic. So if the kinetic is good, reasonable, then you can make use of the thermodynamic and the kinetic K to determine the activation energy. Okay, so activation energy will tell you how easy, how difficult the reaction can take place. Okay, so combination of thermodynamic and kinetic is very important. That's why all chemists have to learn, have to understand basic concept of thermodynamic and kinetics. Okay, next slide. All right, now these are the evidence of dissociative mechanism. We have discussed from the kinetic, we have discussed the thermodynamic. There are other factors like steric factors, okay, and also charge factors. So number of factors that will influence the thermodynamic, that will influence the kinetic, altogether are providing the evidence for your mechanism, dissociative or associative. Okay, I just giving you the concept. Okay, next slide. Okay, I go again on the mechanism using the red concept. Starting depend on the starting complex, depend on the incoming ligand, that will be second order. Okay, and also sensitivity to nature, maybe solvent play important role. Okay, and condition numbers. There's some reaction involve changes in coordination number. So for dissociative, so your ligand is removed, dissociate, and then new ligand come in, give you a new complex. So normally, this first step, equilibrium step, is slow, and the product step is fast. That is dissociative, and we make use of first order kinetic to prove it is a dissociative. Okay, next slide. So this slide show you from the thermodynamic and prokinetic, you can calculate the activation energy, okay, EA. So those who study catalysis, activation energy is very important, and the enthalpy. So these two parameters, kinetics and thermodynamic, will provide you the activation energy and also hydration, enthalpy, yeah. Okay, next slide. So we just look at the kinetic studies. This is a reaction effects of entering ligand. So what you do is you study the rate constant, vary the ligand. So if your ligand increase in size, it must affect the rate constant. So if the rate constant vary with the charge play important role. So from here, it will tell you either it is associative or dissociative. Not only from the rate law, but also the effect of the ligand in terms of size, in terms of charge, in terms of steric factor. But size means related to the steric factors. Okay, next slide. So the detail your docent will discuss with you. So another case is here. Again, you have a case for ruthenium and some other complex, which is labile and inert complex from kinetics, and vary the ligand, provide you all the evidence from kinetic, activation energy, and the enthalpy. You can tell also whether it's associative or dissociative. So to prove associative and dissociative, you need a thermodynamic data combined with kinetic data. That's what I'm trying to tell you. Thermodynamic and kinetic are very important study for establishing the mechanism of the reaction. Okay, next slide. Okay, so we have discussed about substitution in octahedral. But what about other geometry like square planar? So square planar, if it is associative, the ligand will come in here and form a pyramidal intermediate or trigonal bipyramid. And the rate law, okay, first reaction is the reaction of the complex with the ligand, with the solvent, so flexibility, and then the Y factors. So then you have to find the final rate law, whether the final rate law involves two reagents or one reagent. So this definitely is second order. This definitely first order. Okay. So it's the same technique for the square planar. The only difference is in octahedral, if it is dissociative, one ligand is moved. So from 6 it becomes 5 coordination. If the ligand come in associative, from 6 it becomes 7 coordination at the interchange. For square planar, it can become 5 or it can become trigonal bipyramid. So that is the thing. I hope you can see that. You can imagine what is taking place in the reaction. Okay, we go to the next slide. We are coming to the end now. Okay, next slide.
This is the last slide.
Yeah, okay. Okay, so I can now summarize, yeah. So we can discuss, we have discussed about the complex, the type of reaction, substitution reaction. We study from the change in the color, almost all situation in the substitution reaction involve a formation of the intermediates. So you should know this scheme, the reaction scheme, involve intermediates through free equilibrium. Then the intermediate will dissociate giving you the final product. These are the very common scheme in substitution reaction. The formation of the complex intermediate can be slow, can be fast. So in most cases, it's slow, but the formation of the product is very fast. So from this scheme, you can write the kinetic equation. And that equation, depending on the condition of the reaction, will give you second order or first order. And then you do kinetic experiment. If that condition, you do kinetic experiment is first order, then you know it's the dissociative. If second order, then you can tell it is a dissociative mechanism. I think I cover the basic concept when you study overall aspect of substitution reaction, from the reaction itself, stoichiometry reaction, what happening, reaction scheme, and then from there you can predict the dynamic, and then you can combine with the kinetic. So at the end, you will come up with, yes, it is dissociative or it is dissociative. At the interchange, it's just for you to understand that something happened at the interchange. Maybe change in geometry. And I do not want to focus on that because there involves a lot of discussion. But the obvious one, dissociative, using the kinetics, using the thermodynamics. Okay, I think I talked long enough. If there is any question, please welcome for the question from the student. Okay, you see?
Yeah, Prof. Thank you very much for the complete presentation about mechanism reaction of substitution. Okay, students, mungkin ada yang mau bertanya, silakan in Indonesia. Oh, Gregoria, ya. Gregoria ada pertanyaan, Prof.
Ya, silakan.
Good morning, Prof. Thank you very much for the explanation. I have a question. Is the steady state hypothesis used in the actual reaction? Does it really represent what happened in the experiment?
Okay. First, you have to understand the reaction scheme, okay, for substitution reaction. It always involves the intermediates, okay? The intermediates can form very fast, can also become very slow. If that intermediate is slow, that will be the rate determining step, meaning that rate will determine your reaction kinetics. If it's very fast, then the product is slow, okay? But in most cases, the intermediate form very fast, meaning the K equilibrium is big. The Le Chatelier principle, thermodynamic K is high. So then big K means the degree of formation is very favorable, but the rate you cannot predict. You have to see, you have to measure. So, or you can make prediction. Okay, nowadays prediction is very easy to make. You can calculate. So calculation becomes very important. So when you have a scheme, other people can also have a scheme. So which scheme is correct? So it's a question of you make your thermodynamic calculation, you study the kinetic, okay? Kinetic must be followed by experiment. I'm trying to explain now. So when you have a scheme, there is intermediate form. It's not very easy to determine the concentration of the intermediates. Apa istilah dalam bahasa Indonesia ya? Petengah ya. So what you can do is to know the concentration of the intermediate, because in kinetic study, concentration play very important role. Your rate depends on the concentration. You have the concentration of your starting material. Now you have the concentration of your intermediates, okay? And you can determine the concentration of the product. At the initial stage, the concentration of your product is 0. As time goes by, the product become more and more and more, okay? So kinetically experiment, you can determine the reduction of your reactant concentration. You can determine the concentration of your product. That is for experiment. But for the scheme, the intermediate, no way, you cannot determine the concentration of the intermediate. So the only thing you can do is you try to approximate. You have to do the calculation. Because from the scheme, you have to come up with a rate equation, the rate law. So you apply steady state approximation, we call it. Or some people say steady state hypothesis. The hypothesis is the change in the rate of the intermediate is 0. Meaning there is no change in the rate, okay? There's a change in concentration, but the rate is the same. No change. And almost 0. So they use this concept of steady state. Steady meaning is the same, no change, okay? So from that concept, you can determine the equation of your intermediate concentration. Once you know the equation for the intermediate concentration, you can substitute into the rate equation. And finally, you end up with a final rate law. So that is the purpose of steady state approximation. Is just the way you can obtain final rate law. Your final rate law must contain concentration of your substrate, okay? And maybe sometimes your acid concentration, you know, it can become complicated. But what important thing is the final rate law must have concentration that you can determine or you can calculate, okay? So that is the concept. So those docent who mengajar kinetic theory can explain this on detail. I know students normally not very good in the mathematics, will have a problem, but they should know the concept of this, because reaction can be very complicated, like polymerization reaction. You apply this concept in polymerization in many situations. Okay, one more concept is that the reaction may involve one step, may involve many steps. For coordination compound substitution, it already show you the scheme involves 3 steps. One is the formation of your intermediate, and then your intermediate is reversed, and the third step is the intermediate from product. So at least 3 steps. So if the reaction got only 1 step, we call it elementary reaction. Only 1 rate constant, only 1 K rate constant. So if the reaction have many steps, they can have many rate constants, K1, K2, K3. That we call a composite rate constant, okay? So in the reaction study, these 2 situations, one is called elementary step, and the other one is the composite or complex reaction. So complex reaction consists of many elementary steps. Therefore, you have to determine the rate constant of each individual step. And this individual step can only determine by mathematics. But of course, the overall rate constant, you must get it from experiment. So I hope I've explained to Who? Zahra, is it? Okay.
Gregoria, Prof.
Oh, Korea. Okay.
Yeah. Okay, Gregoria, is it clear for you? Yeah, thank you, Prof. Yeah,
Okay.
it's enough. Oh, Gregoria. Ya, jadi memang harus ini ya, Prof ya, untuk mempelajari mekanisme coordination chemistry kita perlu combine mungkin ya, combine laboratory experiment and computation maybe.
Yes, computation.
Yeah.
Nowadays is the computer programming is so advanced. You can do simulation. So the simulation is a good thing when you teach student kinetics. Okay.
Yeah.
But they have to understand the basic. Sometimes the student enjoy simulation, but the basic concept is somewhat less. So yeah, it's effect on the concentration play important role in the rate of the reaction.
Ya, oke. Angel mau tanya ya tadi ya, Angel. Angel tadi raise hand.
Ya, Ibu mau tanya.
Oke, silakan Angel. Mau tanya langsung? Silakan.
Yeah. Good morning, Professor.
Good morning.
Yeah, my name is Angelica. I have a question to ask, but before that, I'm sorry if it already explained. So the question is, can the ligand spectrochemical series be the guide to determine what kind of ligand can replace another ligand? For example, maybe...
Repeat your question again, please. I can't hear it properly.
Can the ligand spectrochemical series be the guide to determine what kind of ligand can replace another ligand?
Okay.
For example, maybe strong ligand can replace the weaker ones, or can it be inverse, or there is another guide? Thanks in advance, Professor.
Okay, I can explain in a different way. When you study the kinetics, you have your complex, you have your ligands, all right? So you study one reaction with one ligand. And then you study the kinetic or thermodynamic, different ligands. That ligand may have different size. For example, chlorine, bromine, iodine, they are different size. So if you have a reaction of ligand coming of different size, you can think whether bigger size can make the reaction difficult or easy. Okay, so the point is it will affect the kinetics of the reaction. So that's one, the size, the steric factor. So the steric factors, if your ligand inside the complex are inert, not easy to be replaced. Number one, you can tell from the kinetic. Sometimes the ligand in the complex, one particular ligand, is bigger than the rest. So when you bring in new ligand, so which one will be replaced? Is it the bigger ligand or the small ligand? So that is one. Then you have to consider the direction of the substitution. Is it happening at the equatorial position of your octahedral complex or at the axial position? All this information you already got from your reaction studies. You will find that from your reaction studies, from the synthesis, you will find only one ligand is replaced. Maybe the big one is replaced. So if the big one is replaced, then you can say, okay, the big one is so steric factors, it will be removed first. Okay, so then you can simulate from your thermodynamic studies, and then you can study the kinetics. The kinetic will tell you, okay, big ligand will be removed, and the kinetics is correct constant is higher. So these are the combination of the kinetics and thermodynamic and charge factors, you can apply your ligand field stabilization energy to explain the behavior, the sensitivity of the substitution reaction with respect to your ligands, ligand size, ligand charge, ligand density. It becomes the entire study. So today, when you do S2 and S3 on kinetic studies, you have to consider all these factors. And sometimes solvent very important also. So if you do in methanol, methanol can solvate the complex. Methanol can complex with the metal. That will make the kinetic behavior slightly different. So what I'm going to tell you is, the book will tell you the answer. So what I would prefer the student to think the effect of steric factors, electronic factors. These are very common factors which will influence the kinetic, influence the thermodynamic properties, and influence the mechanism. Okay, then you can go back and look at the result because there are many studies, many reports. You can read the report. Does the report agree with what you think from the basic that we have already discussed today? Okay?
Yeah, okay. Is it clear, Angel?
Ya, Ibu sudah terjawab. Terima kasih.
Yeah, Angel.
Yeah.
Okay.
There are a lot more. There are lot more questions, yeah, because it's not a straightforward. It's not a straightforward answer.
Ya, jadi banyak pertimbangan ya, Angel ya.
Yeah.
Ligand itu tidak hanya dari deret spike
Satu
protein.
lagi, because your complex is ion,
Ya.
ionic strength also very play important role. Saya harap mahasiswa tahu kan, ionic strength, divide rule. So there are many factors. Yeah.
Okay. Yeah. Now next question from the April. The April, silakan.
Okay, thank you. Kedengar suaranya?
Ya, suaranya kurang jelas. Coba agak dekat.
Apa sudah terdengar, Bu?
Ya.
Okay. Good morning, Professor.
Yeah.
Thank you so much for the opportunity. So my question is that the interchange mechanism of is applied for the planar complex. Or
The voice is not very clear.
Ya.
Yeah.
The April bisa ditulis di chat room mungkin?
Okay.
Ya, tulis dia di chat room ya.
Yeah.
Oke. Mungkin sambil nunggu di April tulis chat, ada pertanyaan. Mungkin dari dosen ada pertanyaan. Pak Uji mau bertanya, Pak Uji? Pak Uji, apakah mau bertanya? Ini ada dosen tamu nih, Pak Uji.
Belum, Bu. Masih menyimak.
Iya. Oke. Ya, ada lagi yang mau tanya? Velia mau tanya, Velia?
Di Unpad ada yang pakai kinetik tak?
Di Unpad yang pakai kinetik siapa ya? Di lab analitik ada nggak ya, Pak Uji ya?
Lalu ini yang pakai kinetik.
Belum, Bu, belum ada.
Belum ada ya?
Belum ada.
Kinetik nggak, Pak Yuda? Katalisisnya?
Yeah, kinetic may be applied for catalysis, Prof. It is possible to be applied in the near future.
Ya, orang yang buat S3 on kinetic, katalisis mereka ada banyak pengalaman yang boleh membantu mahasiswa ya. Kebetulan saya S3 kinetic on palladium catalysis.
Palladium, Prof?
S3 saya is on kinetic study of palladium to catalysis.
Oke.
Jadi saya ada pengalaman lah on kinetik.
Dengan
Ya,
Prof. Untuk reaksi apa, Prof? Dulu palladium.
Palladium itu untuk reaction menukarkan
Ya,
olefin kepada
olefin.
keton.
Ah,
Dan dia masalahnya ialah palladium itu bila harus ada air, tapi olefin itu kan tak larut dalam air. Jadi you have to use mixed solvent, water and organic. Jadi bila you tukar olefin kepada keton, the oxygen come from the water.
iya.
Masalahnya ialah apabila ada water, reaction berlaku, palladium itu jadi palladium zero, jadi metal. So it is an oxidation reaction. How to make catalysis? Itu cabaran PhD saya. 1 tahun, saya hampir give up. Jadi kita study kinetik, gunakan gas intake, homogeneous, ya, begitulah.
Ya,
ya,
Prof.
oke, Prof. Ini pertanyaannya sudah ada di kolom chat, saya bacakan ya.
Ya.
Good morning, Prof. Thank you for explanation. I have question. Maaf jika bertanya dalam bahasa Indonesia. Ini dari Velia. Pertanyaannya, bagaimana cara memilih ligand yang spesifik untuk suatu unsur tanah jarang tertentu agar dapat terpisah 100%? Wow, unsur tanah jarang nih, Prof.
Bagaimana apa?
Unsur rare earth element. Jadi apakah ada ligand yang spesifik untuk satu jenis rare earth element gitu supaya bisa terpisah 100% kan rare earth element sulit terpisah ya, Prof ya?
Ya, oke. Pertamanya macam orang yang mau extract gold ya. Remember last time you extract gold. So you extract gold from the raw. First, you dissolve the gold in the acid. They use cyanide acid. Okay, so the gold will dissolve in cyanide acid and membentuk gold cyanide. Okay, itu sebab itu lombong-lombong timah itu bahaya. Sana ada banyak cyanide acid. So it become a solution, very fast solution, yeah. And then you have to precipitate the gold. You do hydrolysis, okay. So you get, you have to understand gold is D berapa, D3, D4. Kemudian masuk cyanide ganti. Kemudian how to precipitate? You do hydrolysis. So then you separate the gold from the solution. So you can study, of course, the thermodynamic, the kinetic, but at the end depend on your objective. If your objective try to separate the gold, then you have to think of the reaction which can precipitate the metal. And normally hydrolysis, just like in copper just now, you react with ammonia. The first part you got precipitate of calcium of the copper hydroxide. But you have more ammonia, the precipitate will dissolve, okay, and form you the final product. So same principle is or can be applied for separation chemistry. I hope that will answer the question.
Ya, baik. Ya harus ada reaksi-reaksi tertentu ya untuk precipitation unsurnya. Baik. Ini sudah mau jam 10 tapi ada 2 pertanyaan lagi. Mungkin ini yang 2 pertanyaan terakhir ya karena sudah mau jam 10. Baik.
Saya pun hydrolysis sudah mau habis.
Oh iya. 2 lagi ya, Prof ya. Sebentar, Prof. Metode apa dari Jennifer ya, metode apa yang biasanya digunakan untuk menentukan geometris nyawa kompleks intermediate secara teknis? Apakah harus sampai ditentukan struktur kristalnya juga gitu?
Metode apa katanya?
Ini apakah unsur yang senyawa kompleks yang intermediate itu bisa diperiksa juga struktur kristalnya gitu seperti yang produk akhirnya gitu?
Intermediate ya.
Iya, intermediate tadi.
No way. Intermediate bergantung kalau intermediate itu stable, it is stable, you can isolate the intermediate Itu bisa. But in most cases, the intermediates are dynamic properties. The intermediates are what you call it, undergo a series of reactions, series equilibrium. That's not possible. But you can detect the intermediate. You can do UV in nanosecond. There are UV in picosecond. So you can detect the intermediate, but to isolate the intermediate is a challenge. If the intermediate are stable, you can isolate. Thanks God, that's very good. But in more cases, no.
Yeah. Difficult, yeah. Ya, yang paling mungkin adalah dengan UV vis yang apa tadi Prof, second ya? Ya, yang second.
But the final product is always stable. You can study, you can make analysis.
Oke. Iya, satu lagi tadi dari April ya, yang tadi suaranya nggak jelas. So my question is, does the interchange mechanism just occur in square planar complexes, or maybe it can also occur to another form of complexes? If it can occur, what the difference between interchange mechanism in square planar complexes and another form of complexes? Thank you in advance, Professor.
Okay. Interchange means what happened at the interchange. For example, like you drive a car, you stop at the toll. You know toll, where you pay the fee. Yeah. You do interchange with the girl there. You give them money, they let you go through. Okay. So in the case of substitution reaction, because substitution means new ligand coming, ligand inside the complex leaving the group. So either they come together, interchange, leaving the group, or the group leave the complex first, and then the new ligand come in. So what actually happening in interchange? If it is associative, then there will be increase in coordination number. There will be increase in the geometry from 5 to 6, from 6 to 7. So if it is dissociative, you lose one ligand, then the geometry will change. So if it is square planar, one ligand come in, it becomes 5. 5 coordination number means either it is pyramidal or trigonal bipyramid. Okay, that's very easy to understand. Okay, that part, but the kinetic part is not easy. So that's what at this stage, I don't want to discuss the kinetic of the interchange, but they have to know the interchange is one idea from the American side. Okay, if you read the story, the American always want to be different than the British and the German. Okay, so what the student have to understand first, associative, dissociative, and this can be proven from thermodynamic and from kinetic. If you want to discuss about the at interchange, then interchange means at the intermediate. So at the intermediate, to determine the concentration of the intermediate, it's not easy. You have to use approximation. So if you want to know the structure of the intermediate, you can only think one is increasing coordination number, one is decreasing oxidation number. To make it quantitative, then it's a big challenge. So it's good a student able to think what's going to happen at interchange. That's an achievement for me. At least they think what happened at the interchange. Okay, that's my answer.
Yeah, okay. Ya, jelas ya di April ya. Okay. Yeah, thank you. Yeah, okay. Yeah, okay. I think the time is up.
Okay.
Thank you very much once again.
Yeah, my dialysis also just finished.
Yeah, okay, Professor. Yeah, thanks for the attention also.
Okay, maybe one day if I can fly to Indonesia, I come down to Bandung again.
Okay.
But I'm having I don't have any vaccine.
After the pandemic.
I don't take vaccine. That's my problem.
Yeah.
Semoga cepat sembuh, Prof.
Ya, alhamdulillah
That's
so far okay. I'm okay.
Ya, sehat selalu, Prof. Oke,
Terima
see you
kasih,
maybe.
Prof.
Terima
Okay,
kasih.
thank you.
Ya,
Assalamualaikum. Bye bye.
Thank you.
Waalaikumsalam warahmatullahi
Warahmatullahi
wabarakatuh.
wabarakatuh.
Ya,
Good
ya, saya akhiri ya pertemuan kali ini, mahasiswa sekalian. Semoga tadi yang disampaikan oleh Prof. Bohari bisa lebih membuat kita lebih mengerti ya tentang reaksi, khususnya reaksi substitusi dalam kimia, senyawa kimia koordinasi, senyawa kompleks koordinasi, ya kompleks logam. Ya, kita akhiri ya. Alhamdulillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih, Bu.
Ya, diakhiri ya, end meeting.